Nice to be in orbit.
Our technology, in 40 years this year of working in semiconductors, it's very, very difficult to compare one technology to another. How do you compare one type of semiconductor to another? They're good for different things. How do you compare a Ford to a Mercedes? Well, people buy both, so it's just very difficult. But after 40 years, I've actually been able to reduce to a single chart that can compare any technology to any other technology. It's complicated. I'll spend some time on it, so I want you to pay attention. This is what I call the universal technology slide. And this is it. You've heard it from everybody, hence the universal. So the entrepreneur, if you don't believe this, you're not ready. You might be an entrepreneur, but you don't have the right topic yet. Because there's actually two important pieces of information here. One, you have to be absolutely convinced that yours is better than theirs. You have to believe that. Even under bad news, even when you run out of money, even when you get kicked out of a fab, you still have to believe you are better than they are. Almost as important is you also have to believe that they are worse than you are. Right? So there's two axes, there's two pieces of information here. So you have to be able to explain this to your future partners, your future manufacturing, your supply chain, your customers, all those people who give you that information through the capital system, whether they're investors or buyers or partners or co-developers. You better be able to explain the universal technology chart to them, and make sure you scrub this before you give up your day job. Hi, I'm Ron. I'm a CMOS-aholic. I pushed my first CMOS wafer in 1973. In 1973, there was one and only one user of CMOS. It was called the U.S. military. The U.S. military actually saw it as a technology in reserve against the Cold War, the evil Russians. They had 50,000 main battle tanks, actually true. We had 5. But what we had was 50,000 smart battle tank eating missiles, and they didn't. So as long as our missiles were smarter than their tanks, we had the famous mutually assured destruction, and missiles are way cheaper than tanks. So it was a technology war, from the Trident missile to CDMA that was developed at Linkabit for surreptitious communication. It was a technology war. And CMOS, when I used to work for the Navy, I have some of my old Navy colleagues here, we actually felt it's great news that CMOS is absolutely hated by the industry. Andy Grove was quoted as late as 1980, "We'll never use CMOS, ever. I'm going to replace a nice fast NMOS with a stupid slow PMOS that's twice as big. Oh, and it latches up? Really? Twice as many processing steps? I already can't yield this stuff." By 1983, he was on his knees in front of IBM begging for CMOS, and had to give 30% of his company to IBM to get CMOS technology. But before that, it was this slow, dumb, expensive, latch-up, ridiculous, interesting lab experiment called CMOS. But the military loved it. Why? Remember those tank-eating missiles? They needed pattern recognition. They needed sophisticated guidance. They needed eventually a GPS receiver. And I attended a meeting once at the Navy lab. Terry, maybe you were there. And it was, I believe, right after the Falkland War. And there was an admiral. He had one of those arrays of awards that actually went up over his shoulder. It actually looked like a kitchen towel. It was so big. And the guy gets up and he says, "Gentlemen, you have done an incredible job." The Navy lab was one of the absolute early pioneers in digital signal processing, mostly for sonar. They could pull the sound of a cavitating propeller from the SOSUS system from 100 miles away and screen out all the whales and the clicking shrimp and all that stuff. These guys, the technology was incredible. This guy gets up and he says, "Gentlemen, ladies, you have created the capability for us to accurately put a dent in any ship in the ocean. We can hit it, and we can hit the one we want. But the electronics consume so much power, it runs so hot, that we have such a big cooling system in there that there's no room left for a warhead. So we can bink it, but we can't boom it. And I thought, you guys need CMOS, because they were using emitter-coupled logic, which is a good way for a space heater. The computer's this big, the cooling tower's out back. Ask Cray. So CMOS was this idiotic, expensive, complicated, latching up technology that, oh, by the way, didn't consume any power, at least except when it switched. But by any other standard, it essentially was looked at as almost a non-thermodynamic machine, which is how can it possibly do any work and not consume any energy? It turns out it can't. But it was orders and orders of magnitude better than anything else anybody had ever come up with. The military grabbed onto it. Everybody else rejected it for cost reasons. And that goes back to that earlier comment. If you're going to think about starting a company, cost isn't on the list. Performance is. Value is. What are you going to do? Everything was too expensive, including what is now the almighty CMOS. 99.69% of all transistors ever made were CMOS. It used to be rejected, too expensive, useless. CDMA, early on, go read the newsprint. It's too expensive. It'll never work. It's too linear. It's hang a transmitter in your tree and bring down your system technology. But it got there, not because it was cheap, but because it used a more valuable resource than money, which was radio spectrum. The value is there. Forget about cost. You have to, if you want to drive down cost, there's only one thing that drives down cost: volume. Whatever it is, lithium batteries, guess who developed it? The Navy lab down the street. Why? Because they needed that space for warhead in those torpedoes. That's where lithium batteries came from, is torpedoes. They were so friggin' expensive at that time. If you just said, hey, do you think you might use one in a $200, $100 consumer device? No way. Everything's lithium-ion batteries now. Why? Volume. Volume gets you on that exponential growth curve, which says I can make more money if I can get my costs down. The volume absorbs all my overhead costs and my manufacturing costs. It's worth it for me to actually get a more efficient process because of the volume. If I'm not going to have the volume go up, why would I spend some money to make something cheaper? I'm not going to make any more money. This was the technology when I started. I have done everything from indium phosphide to cadmium sulfide to lithium tantalate. I'm kind of a materials device junkie. When I saw the first CMOS idea, I literally looked through the microscope, saw what it looked like, and thought, this is going to take over the world. There's no way anybody can compete with this because it is so low in power, and therefore you can scale it and scale it and scale it, and that turned out to be exactly what was needed for Moore's Law to stay alive. If we didn't have CMOS, Moore's Law would have ended in the 1990s because of cooling problems. The 386 computers were catching fire. You couldn't cool them. There was no way to cool them. They just burned literally their sockets. So without CMOS, the technology really would have died. Here's bulk CMOS. Here's what we do, which is this is not to scale vertically. We actually, when I was at the Navy lab, I was fortunate enough to be the branch head of the Navy's R&D microelectronics group. And I always say that what happened was when IDT left HP, they were the first startup company based on CMOS. There was literally an emergency meeting at our lab, and all of the brain trust of the Navy said, what are we going to do? Because if CMOS goes public, in 10 years the Russians have it. They'll still have 50,000 tanks. They can smarten them up. And then the balance of terror is actually really at risk here. So that brain trust put on a little pachinko ball the question, what's after CMOS? And they dropped it into the DoD pachinko machine, which is 485,000 little buttons, and it bounced around, I don't know for how long. And literally one day it came out of the little chute over my desk. It landed on my desk. And the question was, what will we, the DoD, do in 10 years if CMOS goes public? And I thought, that's a really good question. Wonder why they asked me. I was 25 years old at the time. I didn't have a clue. So I thought, well, maybe I'll go look into why did technologies change in the past? After all, NMOS wasn't the first technology, nor was PMOS, nor was I2L, nor was ECL. The first technology that received the Nobel Prize was RTL, a transistor with a resistor. It was basically an analog gain block used as a flip-flop, and that got the Nobel Prize because the resistor and the transistor were integrated. It did lead to the integrated circuit, but that technology quickly ran out of the ability to scale because it consumed too much power. So I went back and I plotted, forget how many transistors are on a chip every year. Wonder what it looks like if you plot the power consumption of the best chips by year. And instead of being the straight line that was Moore's law, is Moore's law, it turns out it's a sawtooth. It goes up, you use the technology until it hits right around 5 watts per chip, because that's about all you can air cool. After that, you got to start doing something else. You have to do mounted fans, you have to have blowing, you have to do water cooling, you have to do something to cool these things, or the chips just fail. So you go RTL, then you replace the resistor with a diode, DTL, then you replace the diode with the transistor, TTL. You run it from typically a 10x reduction in power. You run it up until you put 10 times as many chips. It consumes too much power, and you replace the diode with the transistor, and then you discover Schottky clamping. Anybody remember TTL-LS? The S stood for Schottky. It was brilliant. It was another one. Then there was I2L and ECL and PMOS and NMOS and VMOS and DMOS and ABCMOS. And in that bag of tricks was CMOS. So I thought, that's interesting. Power is why people change, because they can't continue to use. Nobody retools a whole industry because they want to. They only retool an entire industry because they have to. And they had to when the chips were failing, which means they were overheating. So I thought, well, let's see, CMOS, wow, this instead of a 10x was a 100x improvement. But if I take Moore's law and apply it to that button and draw it out, it turns out in 1989, CMOS will hit the power consumption crisis of every other technology before it. Remember, at this time, CMOS is this idiotically low power-free system. Nobody believes CMOS would ever hit a power consumption because it was so much better. And in 1989, the 386s started burning up. And they had to go from 5 volts to what? 3.3 volts. In other words, gee, take those numbers and square it. Guess what? That's, again, one of those sawtooth things. So then we went to 3.3 volts and 2.5 volts. And we're down to what? 0.7 volts and all these incredible advancements in CMOS. But every one of those is a new tooling, new design tools, et cetera. So when I looked at this guy's problem, I said, we got to do something that's lower power. It's not about speed, it's about power. And so the only way to really dramatically reduce the power consumption was to get rid of the capacitive, the capacitors under these junctions, which on a real drawing would be huge. And charging and discharging those capacitors is what causes the CV squared F problem. And that's why everybody tried to do SOS for exactly that reason. You get rid of the capacitors, it goes faster. You get rid of the capacitors, it uses less power. It sounds like snake oil. I promise if you just take a drink of this, not only will your rheumatism go away, I mean, it was like, how can something go faster and consume less power? That's why all those companies tried to do this. The physics is compelling. The yield was awful. It was so expensive, it wasn't useful. If you look at other processes that are used, especially in RF, you have silicon germanium, which is a bipolar, integrated with CMOS, so you have silicon germanium by CMOS, but it still has the CMOS problems. And this is a bipolar. So it's good for certain things, but it isn't good for switching. And again, 99.99999% of all transistors ever made, they switch. They don't amplify, they switch. That's what a digital computer does. It goes from 0 to 1 and 0 to 1. It doesn't care about the in-between state. In fact, it wants to get between 0 and 1 without ever seeing an in-between state. It would love to be a vertical line, but it just can't do that. So if you really look at the world of electronics, it's made up almost entirely of switching things and a few amplifiers so that we can hear the results or transmit some power. And in order to do that, this is one of the truly great inventions, was the gas HPT, invented up the road by TRW. Thanks to the Department of Defense funding. It's a magnificent amplifier. It makes great power amplifiers. Bipolars just don't make switches, so it's very good for certain things, and each of these technologies has their space. But this is the one that I believed would replace CMOS for that military function. And I believed if we could fix the yield problems on this and do that in a way it would go into a commercial fab, then we could solve the DoD's problem. And so my job, and I got the funding for 10 years, was to find a way to make this commercially viable in a commercial fab at commercial yields so the military could use it.